Hi guys, so today we're going to be looking at Chapter 4, Section 8, Analyzing Graphs of Polynomial Functions. So, the first thing we're going to talk about are turning points. An important characteristic of graphs of polynomial functions is that they have turning points. And these are corresponding to the local maximum and minimum values that are provided. Local maximum value is always the highest point near the nearest points around it. Sometimes you may have multiple local maximums, but in this case we only have one local maximum where we have a peak that's rising up. A local minimum is going down and it's always the lowest point. There are possibilities of having multiple local minimums as well, but in this case we only have one where the peak is going downward. And so there are a few rules to turning points in a polynomial function that we should check out. So the first rule, the graph of every polynomial function of degree n has at most n minus 1 turning points. So what that means is that, let's say you have the polynomial function f of x equaling to x to the power 4 minus 6x squared plus 9. And we have our degree, which is 4. That means that I can have at most 3 points, or 3 turning points, because if our degree is 4, that would be considered my n. And if we're supposed to have n minus 1, that means that we can only have at most 3 turning points. And in this case, let's see, we have 1, 2, 3 turning points. Cool. So with any degree, depending on if you have a degree of 10, for example, you can have at most 9 turning points. If you have the degree of 100, you can have at most 99 turning points. And so that's the rule that we like to follow when we're looking at turning points. Another rule that we have is if a polynomial function has n distinct real zeros, then a graph has exactly n minus 1 turning points. So this case, it's not at most, but instead we have exactly. We know exactly how many turning points we should have. So if we have our polynomial function x to the power 3 plus x squared minus 14x minus 24, and I were to find out all my solutions. Turns out I have 1, 2, 3 real solutions. Then that means that I have exactly 3 minus 1 turning points. So 2 turning points at most. And if I were to check it out, right here we got 1 and 2 turning points. Cool. So it's always good just to know the difference between the two. We are going to be estimating coordinates and kind of identifying and analyzing the polynomial functions that are provided to us. So let's look at this graph right here. If you notice, we have the points here, -1, -1, -2, -3, -4. The range for this one is up to 10, so this would be considered 5, and this would be considered 10. Over here is 5, 10, -5, -10, -15, and -20. On the side, we have 1, 2, 3, 4, 5, and 6. 4, 5, and 6 there. So right here, we're asked to estimate the coordinates of each turning point, state whether each corresponds to a local maximum or local minimum, then determine the intervals for which the function is increasing or decreasing. So let's look at how many turning points our graph has here. I can identify that we have 1, 2, 3 turning points. We have 2 minimum values, order pairs, and 1 maximum value. So I would say right here, we have 3 turning points. The local maximums, I have to round it because they're not giving us really exact points here. So I have here local maximum, which is identified over here on the top. I can round it to about, I would say that looks like 1/4 or 1,4, somewhere around there. The local maximum here, it's kind of like between 0 and -1. So I would say this is negative 0.5. And it goes all the way down to, I would say, -4. And again, this is just kind of rounding it out. There's not really an exact number because we're not actually given a graph that allows us to have exact numbers. The other order pair that we have here is over here. This is another local maximum. This point is kind of like around 3, -14. Okay. And so based off of our order pairs here, I'm going to identify the functions decreasing and increasing. Now, if you're determining whether a function is decreasing or increasing, again, you're going to move left to right. It's always good to identify and know that you're going to be moving left on the x-axis to the right side of the x-axis. So for the order pairs that I have, I'm just going to write and label it just for now to make it easier. So this was considered negative 0.5. I said that this point right here was about 1, and this point right here was around 3. And those were my maximum and minimum values. Okay. So from here, the function is decreasing. The only time I see our image here decreasing is starting from the very infinity all the way to negative 0.5, and also from 1 all the way to 3. So when I write my answer, I'm going to write here that we have x being less than negative 0.5, because I'm looking at all the points that are smaller than 0.5, which considered to be these points, and it keeps on going on and on and on. So it's all the points right here that are smaller than 0.5. I also see right here the decreasing from left to right. So we have here 1 going all the way to 3. So I'm looking at all the points between 1 and 3. The function increasing, I see that it's increasing here and here. So let's start off with this increasing right here. We have it between negative 0.5 all the way to about 1. And the last one that's increasing are all the points that are bigger than 3. So I'll put down that we have all points bigger than 3. And that's how I would analyze my graph. Okay. Another way we can look at our graph or polynomial function is by determining if we have an even, odd, or maybe neither function. It could be even, odd, or possibly neither. Now, the rules for an even function is that a function f is an even function when if you were to substitute your x for negative x, you should still receive the same answer in the end. All the signs should be the same. Nothing should change. If you have a function that is odd, when you substitute the negative x into the polynomial function, you're going to notice that all your numbers and terms should be the opposite symbol. All like the positives should be negative, negatives should be positive. And neither just makes it so that it's not either odd or even. So let's test it out. Determine whether the functions here are even, odd, or neither. We have here f of x equaling to x to the power 3 minus 7x. I'm going to substitute my x value for negative x and see what happens. So if I substitute all my x values for negative x, my new function is negative x to the power 3 plus 7x. So as you can see here, all of my terms ended up being the opposite symbol. And so I would consider this to be an odd function, where we started off with, we ended up with completely different symbols for every single term. So this would be considered to be odd. If I were to look at the function over here, and I were to substitute negative x into it, again, negative x to the power of 4 plus negative x to the power of 2 minus 1. If I were to solve for this, I get here x to the power of 4 plus x to the power of 2 minus 1. And so from here, I can see that all my terms are still the same symbols and like just exactly the same. It didn't change anything even though I substituted by a negative x. And so I would consider this function to be even. Last one, let's try substituting it out with the negative x. And then we get negative x to the power of 3 plus 2. That turns into being h of negative x equaling to negative x to the power of 3 plus 2. And so if we look here, this becomes negative, this is positive, and this one stays as a positive too. So it's not odd, because if it was odd, this 2 would have to be negative. And it's not even, because if it was even, this x would have to be positive. And so we would consider this to be neither. It's neither odd or even. And so that was it. So hopefully this helped. Good luck.